So public key, as I mentioned, it is like email ID. Okay, so you will be having so many email IDs. So with the help of that email ID, you will be able to pass on the message to the other person. So here you can see that in the okay, here you can see the Bob's public key ring. Okay, he is having the public key of Joy, Mike, Alice, and Ted, so on. Okay, so he is having several public keys available. And now he wants to send the message to Alice. Okay, so he is using the Alice public key. Okay, the plain text input is there, and the public key of Alice is taken, and it is given to the encryption algorithm, such as an RSA algorithm, and it is encrypted. So we will be getting the ciphertext. Okay, so this ciphertext is transmitted, and on the other side, now Alice has to read the message. So using decryption, she has to again convert that ciphertext to plain text so that she will be able to read what the actual message is. So in the decryption algorithm, it is actually the reverse of the encryption algorithm. So here she is using her own private key. Okay, that is like her password. So she's using the private key, and she's decrypting the ciphertext, and from that she's getting the plain text output. Okay, so this is the concept of this public key cryptography. So on, and also so this why we want to use this public key cryptography is that this, though it is used for encryption and decryption, it is not always used for larger messages. Okay, this encryption and decryption is only for key distribution. So like how we have studied in symmetric cryptography, where the both the parties will share the same key. So in that case, the key has to be transferred securely to the other party also, right? So in such a key distribution and for digital signatures, this kind of public key algorithms, public key cryptography algorithms could be used. Okay, so the key distribution to have secure communications without having to trust some other third party to for exchanging your key. Okay, and the digital signatures to verify a message. So this also I told you. So we are getting a message, but we should know that it is the sender. The sender is an authenticated person, right? So so whenever we send any message or a letter or anything, we will usually put a signature under that. Okay, so stating that this is written by me, this message is sent by me. Okay, so that is why this digital signature also plays an important part in message authentication. Okay, so so for these two purposes, this public key cryptography is used. Okay, so this the same thing, public key and private key pair, we are using it, and for encryption we are using the public key, and for decryption we are using the private key. Okay, so there are some differences given between this symmetric versus public key. Symmetric is private key cryptography. Okay, and public key is asymmetric cryptography. So in an conventional encryption, we need to have the same key for that is this symmetric key encryption algorithm. We need to have same key for both encryption and decryption. Whereas in public key, we have one algorithm for encryption and another algorithm for decryption. Okay, and the sender and receiver must share the same algorithm. Must share the algorithm and the key. Okay, the same secret key is used, and both has to share the algorithm as well as this key. Whereas here, the sender and receiver must each have one of the matched pairs of keys. So as we have seen in Bob's key ring, he is having all the public keys only. Okay, and along with that, he will be having his own private key also. and the other party will be having his own private key and others public keys. Okay, so one of the matched keys should be available with the person who is either transmitting or receiving the message. Okay, for transferring the message he should have the public key of others, and for receiving it he should have his own private key. Okay, and in the case of security, here in conventional encryption, the key must be kept very secretly. Okay, and also here there is no possibility. So it must be impossible or at least impractical to decipher a message if no other information is available. So without the key, there is no possibility of decrypting the message. Okay, so with the no other information, it should be able to decipher the message, okay, or decipher it and get the plain text. Okay, so only using the secret key it should be able to decipher it. Okay, and here also in the case of public key, here we every person or every entity who is transferring the message will have a pair of keys. One is the public key and another one is the private key. So here one of the keys must be kept secret, that is the private key must be kept secret, and public key can be shared with anyone. Okay, and here also it should not be able to decipher without this private key. Okay, and here the knowledge of algorithm plus samples of ciphertext must be insufficient to determine the key. So what the hackers will do, what the adversaries will do, they will try to assume this key, right? So in the case of security, if you are going for an ATM machine, so whatever it is, so what we are trying to do, we are trying to keep our pin safe. Okay, you are trying to keep your pin number safe. So even if you are lost your ATM card or anything, no one else should be able to access using that. Okay, so it should be kept safely. So what adversaries will try to do is they wanted to get that key, okay, or the secret key that you are sharing between you and a receiver. The adversary or the third party or the hacker wants to get that key. So it should be ensured that the algorithm or some sample of the ciphertext, because anyway the adversary would be able to get the ciphertext, but that ciphertext should not give him a guess. Okay, this might be the key. If the key is like this, the ciphertext will be like this. So that should not be, he should not be able to do any guess out of the samples of that ciphertext and also the given algorithm. I hope you remember the demo that I have shown you for blockchain. There you have seen that even if a single character has changed, the entire hash key will be changing, right? So what it means, even if you are keeping repeating certain part of the text in your plain text repeatedly, the ciphertext will not have the repetition. Okay, so the samples of the ciphertext that the hacker or adversary is getting, with that he should not be able to guess the what the key should be. Okay, so that is how it should be. In the same way here also, the both the one of the keys, though the public key is available to the other person, with that and the ciphertext, you should not be again able to guess the key. Okay, so that is the very important thing in this both symmetric and public key encryption. So this actually this public key crypto system cryptography, it can be used for two purposes. One is secrecy, okay, or the confidentiality, and for another thing is authentication. Okay, so and either this can be used for confidentiality, or it can be used for authentication, or it can be used for both the purposes. So here you can see the source A is going to send the source A is going to send the message to the destination B. So here is the message, and the message X is given to the encryption algorithm. So if you just want to have secrecy of the message, so what will you do? When you want to convert it into a ciphertext, for that the destination B will be having a public key. Okay, so that public key, So this key belongs to destination B. The public key of destination B is going to be used for encrypting the message. So that will give ciphertext Y, that is encryption of the given message, comma public key of the destination. Okay. So with this, now on the receiving side, it is given to the decryption algorithm, where the party is going to use his own private key. Okay, because he is having a key pair on private. So this public key is available with the source A, because this is shared with anyone. This can be shared with anyone. So now this private key is used with the used by the destination or the receiving party, and applied it on the decryption algorithm. So what he will again finally find again the message. Okay, what actually sent by source. So decryption of the given ciphertext, and also along with the given available private key, he is able to get the decrypted text. Okay, that is the plain text again. So this is for for the ensuring the confidentiality or the secrecy. Whereas in authentication, now the message sender has to prove that he is the sender, he is the authenticated person, and he has only sent the message. That he has to prove. So for that, he is doing the he can do it with his own private key, that is doing a signature. Okay, it is like giving a signature on the letter. So the using his own private key, the source A has encrypted the plain text. So that means that the message X is going along with the signature of the owner. Okay, signature of the sender. So now this encryption will give you a ciphertext which carries the digital signature of the sender. So now when it is encrypted by decrypted by the destination, he has to use the public key of this source A to decrypt it, so that now he will understand that this message is authenticated and it is sent by this particular person A. Okay, so that is ensured using this kind of encryption, and it can also be used in both the ways. Okay, both confidentiality as well as the authentication can be also done at the same time. Okay, so you can see here the message text is first signed by the private key. Okay, so that is why the private key of this source A is used, and it is encrypted, and then again it is encrypted by the public key of the receiver. Okay, so that now it is again the first initially he was signing along with his private key, then he is converting into ciphertext with the help of the public key of the receiver. Okay, so now the ciphertext is gained, and when it is received by the destination B, the now both the decryption algorithm has to be applied, so that once the ciphertext will be converted into plain text, also the message authentication will also be revealed to the receiver. Okay, so first he is using the private key of his own pair. Okay, the private key of the destination B is supplied, so that he will be getting a the plain text, and again he is supplying the public key of the sender. Okay, so that will give you the message that it is authenticated one. Okay, it is sent by source A only. Okay, so authentication will be proved at this point, and also he is getting the message. Okay, so now how it is happening? So to get so Z will be actually the encryption of the you are doing it with the public key of the receiver, Okay, for which one? For the signed document. Okay, for the signed message. How you are signing? Using encryption of your own private key with the plain text message. Okay, and on the receiving side, how the actual message is received? What is X? So first he need to decrypt it with the his own with the public key of the sender, and then also to know that it is sent by only that particular sender, he has to again decrypt it along with the private key of his own thing. Okay, so now this will give the both the things, that is authentication as well as the confidentiality. Do you understand this, ma'am? Yes or no? Can I get some response? Are you all in the class? Are you all present in the class? Yes. What about others?
Yes, ma'am.
Thank you. Yes, Jeffrey, Venkata Mukesh, Jabez Samuel. Others, are you all listening? Okay, so these are all the, I'm not getting many responses. I hope you're all listening. So the same thing again. So now this will be, as I told you, either it can be used for providing this secrecy or the confidentiality, and for then in the case of authentication, it is used as a digital signature, and for key exchange. Okay, to share the secret key between two parties, it can be used. And there are some specific uses of these algorithms. We have discussed RSA algorithm, and we are yet to do with elliptic curve. Then we have some other algorithms like Diffie-Hellman, DSS. Okay, so in what are all the ways these algorithms are useful? It is given here. The RSA and elliptic curve algorithm will be used for encryption and decryption, and they are also useful for digital signatures and for also key exchange. Whereas this Diffie-Hellman algorithm, it is only for key exchange. Okay, not for the encryption or decryption, as well as not for digital signature. And DSS algorithm, it is only for digital signature. Okay, so its main purpose itself is only for providing digital signature. So these are some of the applications. So now again we will discuss the RSA algorithm. So let me switch on to the board for showing you. I'll discuss the same example so that you will be able to understand it. So I hope you are able to see the whiteboard. So this RSA algorithm, as I have told you, it is named after the three inventors, Rivest Shamir and Adelman and another person. So this algorithm, how it works, okay? So here in this cryptography, this is a asymmetric cryptography algorithm. That is, it is a public key cryptography algorithm. So as we have seen in the previous slide, this RSA algorithm, it could be used for all the three purposes. You can use it for encryption and decryption, as well as you can use it for the digital signatures, as well as for key exchange, okay, sharing the secret key between two parties, okay. So for that also it can be used. So now how this RSA algorithm works is that the first step is that we need to choose two prime numbers, okay. We need to choose two large prime numbers. So for our convenience and to just know how this algorithm works, we are taking very simple, very small prime numbers, but in actual case it is not so. We have to go for a very large prime number, okay. So now let us consider that let us consider two prime numbers p and q. Let p is equal to 3 and q is equal to 11, okay. Let us take these two prime numbers, p is equal to 3 and q is equal to 11. So the next step is that we need to find the value of n and phi. Okay, we need to find the value of n and phi. So what is the value of n is? So next we need to find n and phi of n. Okay, so n is nothing but n is equal to p into q. Okay, n is equal to p into q. So here in this case it will be 3 into 11, that is equal to 33. Okay, and then we need to find phi of n. This is equal to p minus 1 into q minus 1. Okay, p minus 1 into q minus 1. So what this will be, this is equal to p is 3, so 3 minus 1 is 2, and q is 11, 11 minus 1 is 10. So this will give you now the value of 5. Okay, p minus 1 into q minus 1. And next we have to what is the next step is that we have to find the public key. So since this is a public key cryptography, we need to have the public key as well as the private key. So this RSA algorithm, it helps you to find out both the public key as well as the private key. So this pair has to be found. So now the next step is to find the value of public key pair. Okay. So this public key, it is actually it's going to be the pair that is e comma n. Okay. So now we are going to find, so e or n already we know, but we are going to find out the value of e. Okay, we want to find the value for e. So what is this e value is that this e value should be chosen by us, okay, and how it should be chosen is that this should be a co-prime of the phi value, okay, co-prime of phi of n. So what is the meaning of this co-prime is that the value that you are going to choose for this e, it should not be multiplied. It should not multiply by the factors of phi. Okay. What is the factors of phi? Phi value is 20. Okay. What are the factors of phi? 10. Okay. So actually it can be written as 5 into 4. The 20 value can be written as 5 into 4 or 2 into 10. Okay, and this can also be written as 1 into 20. Okay, these are all factors. 5, 2. Okay, this 4 can be also written as 2 into 2. So 5, 2 are all factors of this value 20. So now the co-prime value, that is the E value that we are going to choose, it should not be multiplied by the factors of this 5 value. Okay, and also it should not it should not also be divided by the 5 value. Okay, it should not be able to divide it by the what is the meaning of dividing by a particular value? It should give the result remainder value should be 0. Okay, but that should not also happen. Okay, your remainder should not also not get 0 when you multiply by this 5 value. So if we need to find a prime value which is satisfying these conditions. Okay, so that is why we gave that condition as this E value should be greater than 1. Okay, it should be greater than 1, and but it should be less than phi of n. This is one condition. Okay, this E should be greater than 1, but it should be less than phi of n. And another condition is GCD of this GCD of E value that you are going to choose and phi of n should be equal to 1. That is, the common factor between these two should be only 1. It should be, both the values should be the common factors. For both of these numbers, the common factor, common divisor should be only 1. Okay, not any other value should be a common divisor for these two. Okay, so these are the two conditions that is given for identifying the E value. Okay, now what are all the prime values? So what is phi of n? Phi of n is equal to 20. Okay, we have found that phi of n is equal to 20. So what are all the prime numbers that are less than this? We have seen that E should be greater than 1 and also it should be less than this value. What are the prime numbers that are available within this range? Can anyone give me the answer? What are the prime numbers that are available that is greater than 1 and it should be less than this 20? What are the prime numbers available? Can anyone give the answer? Yes. You can at least give in the chat box too. What are the prime numbers that are greater than 1 and it should be less than 20? No one? No one knows what is a prime number? Okay, what are the numbers you are giving? Very good. Jominjos and one more has responded. Thank you. So what are all the numbers you have mentioned? Okay, 2, 3, 5, 7, 11, 13, 17 and 19. Okay, so now in this we have to choose a value for E which should be satisfying this condition. Okay, you can what is said, the factors that are present in this phi of n should not be the it should not multiply by the factors of what we can say, it should not be taken. Okay, that factors cannot be taken. So we have 2, 5. Okay, all these are all factors of this phi of n. Okay, so that cannot be taken. And the 3 and 11 are the prime numbers that we have chosen itself. Okay, that also we cannot choose. Okay, so apart from that we have some other values. So now we have to choose between any one of them. So let us take the option for 7. Okay, so with the remaining things we will first will take assume that E is equal to 7. Okay, let us take let E is equal to 7. So now you just check with the condition also. E is greater than 1 and also it is less than phi of n. So that condition will be satisfied. And the next one, the greatest common divisor of this 7 and 20. Okay, GCD of 7 and 20 will be You don't have any other. For this one, it is only divisible by either 1 or 7. The factors are 1 and 7. And here it is 1, 2, 5, and then 20. Okay, these are all the factors. So among this, only 1 is the common divisor among these two numbers. So that is also satisfied. Okay, so let us take E is equal to 7. Okay, now the next step. So now we have assumed that E is equal to 7. So this is what the public key pair. So what is the public key pair is E comma N. Okay, so E is now we have taken 7 and N is we have computed it as 33. So this is the are you able to see that? Okay. So this is the public key we have now found. Okay, so E7 that is E is equal to 7 and N is equal to 33. So this is the public key we have find out here. So E is the actually public key. Now we want to the next step. Okay, the next step is finding the private key. Okay, find the private key. Let us call it as D. Okay, let the value be D. So now we want to find out the private key value D. So how it can be, how this D value can be found is that we have the formula that we have a formula that D into E is equal to sorry, let me write it at the beginning. I'm not able to scroll it down it. I'll wrap this here. So now we want to find the private key. So what is available is that we have a formula that this D is equal to E inverse mod phi of N. Okay, so we have a formula D is equal to E inverse mod phi of N. So this can be written since this is E inverse, then it means that 1 by E. Okay, so when it is taken over this side, we will get E into D is equal to mod, then it is 1 mod phi of N. Okay, now because E value is going there and here you will be having only 1 mod phi of N. Okay, so when you have such thing, okay, when you are having so if you are having any value something like this E is equal to 1 mod phi of N, when these two numbers are co-prime, okay, we have already seen in the previous step this E and mod phi of N are co-prime numbers. Okay, so in that case, so as we discussed, this co-prime means it will be having the common divisor as 1. Okay, only 1 will be the common divisor. So in that case, it is said it is always there exists E inverse. Okay, there will also always be existing E inverse for this. So that can be written as E inverse into E congruent to 1 mod phi of N. Okay, E inverse into E is congruent to 1 mod phi of N. Okay, so now this can be written as, so now what we are having actually is that D into D. So how we are having it is now D into E is equal to 1 mod phi of N. Okay, now this can be written as based on this congruency D into E is equal to mod sorry, DE into mod phi of n equal to 1. Okay, so this congruency can be written as taking this mod phi of n into the left side. This congruency can be changed as equal to. Okay, so the same thing is applied here. DE mod phi of n is equal to 1. So now with this, we will be able to find or assume the value for D. So because what are all the things that we know here is that we know the value for E, and mod phi of n we know, and we want to find what is D. Okay, so this D value, what we can assume here in this case is that, so you just assume it here. So D value we do not know, that we want to find out, and E already we know that, right? E is equal to 7. So 7 into D. D we have to find it out. Mod phi of n is equal to, and phi of n, as you know, phi of n value is 20, right? Phi of n is equal to 20. This is equal to 1. Okay, 7 into D mod 20 is equal to 1. So now you can assume the value for D. What is it said? You are going to multiply some value. Okay, 7 into a value. Mod 20, it should be equal to 1. So what could be the value for D? So mod 20. So if you are keep on assuming the value for 1, if D is equal to 1, 7 mod 20, that is not equal to 1. And if D is equal to 2, 14. 14 mod 20 is also not equal to 1. When D is equal to 3, it becomes 21, right? So 21 mod 20 is equal to 1, right? Because the remainder will be 1. So what we can assume? So now we can take that D is equal to 3. So in that case, this condition will be satisfied, right? So now we have found the private key of this public key cryptography pair. So this is also equal to D is equal to, so the private key will be D comma n. Okay, so it is 3 comma, again n is equal to 33. So now using this, how we are going to encrypt and decrypt the message that you are going to send. So let us assume that the plain text that we are going to send to the receiver is 2. Okay, let the plain text message that we are going to send is 2. Okay, that is P is equal to 2. Now this plain text needs to be encrypted and it should provide a ciphertext. So how will you find the ciphertext here is, the ciphertext has to be found using C is equal to P power E mod n. Okay, P power E mod n. So what is P? P is actually the plain text value, okay, the message 2. And what is E? E we have found it as 7, and mod n is equal to 33. Okay, so now you can calculate this. If you have a calculator, you can calculate and find it out that this value will be equivalent to 29. Okay, so now this is the ciphertext. So now this will be sent to the receiver side. So on the receiver side, now they have to decrypt it and they have to again find the plain text. So how the decryption process will happen? The decryption has to be done and the plain text has to be find out. So plain text is find out using the given ciphertext power D, okay, C power G and mod n. Okay, so that is why we are using the private key pair is D comma n, and here it is E comma n. E is the actual public key, okay, and D is the private key. So C power D mod n. What is C? C we have find it out as 29. 29 And power d. What is d we have found? D is found as 3. Mod n is equal to 33. So again, if you just calculate it using your calculator, it will give you the value as 2, which is the actual plain text that we are intended to send to the receiver. Okay. Do you understand this, ma'am? Yes or no? Do you understand? Can I get some response?
Yes, ma'am.
Yes, ma'am.
Yes. Others, what about others? Can I get some response, at least in the chat box? Yes. Very few responses I'm getting out of 65. Okay, thank you, ma, thank you. So let me take the attendance. So from 12th onwards, your internal exams will start, and this time we will be having a few changes in the question pattern. So far you were used only to multiple choice questions. So from this semester, from this internal onwards, you will also be having true or false and one word answer, and also the match the following. Okay, so please prepare well. Okay, quickly give me the attendance, ma'am. Pragna,
Yes, ma'am.
Neela, Sumant,
Present, ma'am.
yeah, Jomin Jose,
Present, ma'am.
Manoj Preetham,
Present, ma'am.
Jerome Andrew, Jerome,
Yes, ma'am.
Nelson Darius,
Present, ma'am.
Gemini Annie Verghese,
Present,
Gemini,
ma'am.
yes, Sheshandri,
Present, ma'am.
Annie Cruz,
Present, ma'am.
Madhumita, Madhumita, Madhumita is not there. Venkata Mukesh,
Yes, ma'am.
Naveen Kumar, Naveen Kumar, Satish Kumar, Satish Kumar, Preetham, Jaladi Preetham,
Present, ma'am.
Jeffrey Jabastin, Jeffrey, you're answering that time. Okay, Benzam Raj,
Present, ma'am.
Angeline Subakar,
Present, ma'am.
Ujjal,
Present, ma'am.
Lasvita,
Present, ma'am.
Joel Sam,
Present, ma'am.
Steve Abraham,
Present, ma'am.
Aditya,
Present, ma'am.
Devin
Excuse
Jeff.
me, ma'am.
Yes.
Present, ma'am.
Ma'am, Jeffrey Jabastin, ma'am.
Yeah,
I had
I
a
have marked you because you have answered in the chat box. I have answered. I have marked you present.
Thank you, ma'am.
Saumya,
Present, ma'am.
Adina Sneha,
Present, ma'am.
Joseph Rajan,
Present, ma'am.
Karen Beulah,
Present, ma'am.
Christo Saharia,
Present, ma'am.
Divina,
Present, ma'am.
Alex Kuriakos,
Present, ma'am.
Bharat,
Present, ma'am.
Ashish Kumar,
Present, ma'am.
Emmanuel Raja, Emmanuel Raja,
Present, ma'am.
Jabez Samuel, Jabez, Sam Jonathan,
Present, ma'am.
Vigneshwar,
Present, ma'am.
Okay, Jebes Samuel present. Okay. Vigneshwar present. Chinmohan Lal.
Yes, ma'am.
Letitia Miraculin.
Present, ma'am.
Christina.
Present, ma'am.
Christina.
Present, ma'am.
Ashley.
Present, ma'am.
Okay, Ashley. Hayden Rex.
Yes, ma'am.
Sriram Prasad.
Yes, ma'am.
Jemima Elizabeth.
Present, ma'am.
Arsha Anna Daniel.
Yes, ma'am.
Rishabh Nair.
Present, ma'am.
Okay, Rajat Nair.
Present, ma'am.
Manoja Abraham.
Present, ma'am.
Bibia Susan.
Present, ma'am.
Jibi Thomas.
Present, ma'am.
Selvam Abhisha.
Yes,
Selvam
ma'am.
Abhilash.
Present, ma'am.
Don Milton.
Present, ma'am.
Genovin Jabadas.
Present, ma'am.
Darwin.
Present, ma'am.
Lamek.
Present, ma'am.
Maria Santosh.
Yes, ma'am.
Sasidhar Reddy.
Present, ma'am.
Austin.
Present, ma'am.
Kambam Sanjay.
Present, ma'am.
Kevin Paulson.
Present,
Kevin.
ma'am.
Okay. Sri Sai Rahul Reddy.
Present, ma'am.
Kavin. Singham Shetty Johnson.
Present, ma'am.
Sai Srujan.
Present, ma'am. Present, ma'am.
Sriram.
Present, ma'am.
Okay. So absentees are York 18 CS
Ma'am,
216.
18 CS 272 present, ma'am.
216.
Okay. 272. Where have
No,
you?
ma'am, some network issue.
Naveen Kumar, are you
260 also
present?
present.
Naveen Kumar,
Yes,
you
ma'am.
are all joining now only.
216, ma'am.
No, ma'am.
216 Madhumita, Ellaru Iping. Where have you gone when I called you? Were you listening the class?
Yes, ma'am.
Ma'am,
Yes.
last class Friday was present.
Yeah, the lab, right?
Yes, ma'am. Yes, ma'am.
Yeah, I haven't yet marked the attendance. Wait.
Okay, ma'am.
Okay, I'll check. I'll do it. Okay,
Okay.
thank you, students. You may leave the class.
Ma'am.
Yes.
Ma'am, 1 to 2 1. I'm present, ma'am.
1, 2.
2 1.
Kavin. Okay, yeah, present.
Thank you, ma'am.
Thank you, Ma. You can leave the class.